Okay, I don't see His Highness out there, but can one of the organizers give me permission to start? It's all good? All right. Okay, so this is the last session, and so I'll be the chair, and so we'll start with Ronak Soni, who's going to tell us about the holographic covariant entropy bound.
Thanks, Dan, and salam alaikum, everyone. I'd like to start, of course, by thanking the organizers for organizing this nice conference and giving me the opportunity to speak. We've heard a lot of people be thanked, but one more, including Ahmed and Saunders and the AV team. But I also wanted to add a thanks to the people serving us, because they put in probably more work than all of us combined. Yeah. Okay, so I'm going to talk about this set of papers with Aaron, the one that's out and one that is not. It's about the connection between entropy and geometry, right? We all know this famous Bekenstein-Hawking formula, that entropy is something to do with an area over 4G Newton, right? The most precise version, of course, is the HRT formula, which is entropy of some boundary system is the area of some minimal extremal surface. But there's also some idea that it should be more general. And there's a very nice cartoon explanation that you find in a lot of popularizations about why this is more general. And it goes something like this. Suppose I have a surface sigma, okay? And I tell you this surface is a sphere of area A. Then, roughly speaking, area over 4G Newton is the amount of information I can throw into sigma before sigma becomes the horizon of a black hole, okay? Now, this is a cartoon, not incredibly precise, but this cartoon already has two very important and deep facts in it. The first is that area is an upper bound on the entropy. It is not the entropy itself. There is a class of spacetimes with different stuff inside sigma, and the one with the most black hole entropy is has entropy area over 4G Newton. Secondly, it is an upper bound given certain facts about sigma. The first fact is that it is a sphere of area A. The second fact is that it is not inside a black hole, okay? Because we stop maximizing the entropy, we stop throwing stuff in when the surface becomes the event horizon of a black hole. Now, this is a very familiar thing, because this is exactly what thermodynamics is. Okay, in thermodynamics, entropy is a function of macro state, not micro state, right? So, for example, if I have a very large system and I have a state with energy E, whether or not that state is pure or mixed, the thermodynamic entropy is the thermal entropy of a certain temperature, which is a function of this energy E. In particular, it is the maximum entropy among all states which satisfies this given condition. And that maximum entropy state is the canonical ensemble. Even the microcanonical entropy is an example of that. Because in the microcanonical entropy, we maximize subject not only to the energy expectation value, but also the condition that energy fluctuations are small in the large system size limit. Okay? So, in this talk, I want to introduce a similar max-ent question. These questions where you maximize entropy are called max-ent questions, I believe following Jaynes. Okay? And I will present two max-ent questions. And they're secretly the same max-ent question, but I won't explain in this talk why they're the same. You can open the paper for that. One max-ent question will be a bulk question, which is similar to our cartoon, okay? Where we will maximize entropy over space-times. The other max-ent question will be a boundary question, and boundary is in quotes, because this boundary won't be at the asymptotic boundary of some ADS. It will be a Cauchy slice, and there will be a theory on the Cauchy slice, which will be a strange sort of theory, and we will maximize entropy over states in that theory, okay, similar to thermodynamics. And it turns out that they're the same, related by this conjecture known as Cauchy slice holography. That is really the Cauchy slice holography is really the animating force behind this set of work. Okay, historically we did the boundary question first, and then realized that it's the same as the bulk question. But the bulk question is better defined, more rigorously. Sorry, where did it go? The bulk question is more rigorously defined and more accessible, so I will start with that, and then I will explain the boundary question as well. I will emphasize that it is taking this boundary question seriously that can lead to many more interesting things, as much as the bulk question. Finally, I will comment on holographic tensor networks and black hole information. So let me start with the bulk story. So in the cartoon, we spoke about entropy upper bounds. So let me decompose it into 3 steps. The first thing we did was we said that here is a surface sigma. I will define it by the fact that it is a sphere of area A. In other words, I defined it by its intrinsic metric. Second of all, I said, okay, consider a space-time containing this surface sigma, and I defined a notion of entropy of that space-time, which was the entropy of all the stuff inside sigma, or those little books I threw in. Okay, and finally, we upper bounded this entropy. We looked at all space-times with different types of stuff inside sigma, and looked at which one had the most entropy. Okay, so these are the 3 steps. There's 2 definition steps and 1 result step. I will now present a precise version of the precise entropy bound, where we will define all 3 steps more carefully. So I will stick to asymptotically ideal spacetimes with apologies to Alejandra, and further take sigma to be topologically a sphere. Okay, this is for simplicity. There are other cases in the paper. Okay, now in asymptotically ideal spacetimes, sigma is a sphere. There will be a boundary CFT homologous to that sphere. Okay, and the entropy of the spacetime containing sigma is the entropy of this boundary region. Now, if sigma is in a baby universe, this boundary region can be empty, and in that case, the entropy is 0. Okay. So, so in other words, the entropy of the spacetime is the area of the minimal extremal surface homologous to sigma. Okay. So that's step 2. Now we have to come to step 1. How do we define sigma? Earlier we defined it just by its intrinsic metric. Turns out that's not really enough. So let me take a Schwarzschild, ADS Schwarzschild black hole and consider this interior surface to be sigma. Okay, I will define sigma to be any surface with the same intrinsic metric as the surface out here. And this here is the bifurcate horizon, which is the entropy of the spacetime. Now, I can take a flow of spacetimes where I increase the area of the bifurcate horizon and send sigma to be closer and closer to the singularity. And I can increase the area of the bifurcate horizon an arbitrary amount. So if I define sigma only by its intrinsic metric, the entropy bound is infinite. There is no upper bound. Now this is not very interesting, because if I'm going to say the upper bound is infinity, I might as well not talk about upper bounds, right? So we have to be more careful in defining sigma. And the idea is that I will define sigma by all the data on sigma. So in pure GR, this is the intrinsic metric and the extrinsic curvature. So sigma is a codimension 2 surface, okay, like a black hole horizon, and it will have 2 null normals, K and L. Okay, and for each null normal, there is an extrinsic curvature. It is the covariant derivative of that normal with indices on sigma, which is what this equation says. In particular, the trace of this extrinsic curvature is known as the expansion. It tells you how much the area changes when you deform the surface a little bit in that direction. So I will define the surface by its intrinsic metric and these extrinsic curvatures, of course, up to coordinate transformations. This is not the whole story. There is also something called the twist, which is like a gauge field for local boosts around sigma. It's not super important. Sorry, it is important, but I will ignore it. I will take the case without the twist. So with this, we will now find the result. We have defined sigma. We have defined the entropy of a spacetime containing sigma. So what is the upper bound? And yet again, I'll take sigma to agree with the rotationally symmetric surface in some non-rotating PTZ black hole. And the answer turns out to be this. The entropy bound is area over 4G Newton, the well-known and well-loved formula, times this funny square root. The thing inside the square root is the 2 expansions. Each expansion, remember, tells you how the area changes as you deform the surface. So let's take some cases, because this is a bit cryptic. So let's take a surface outside the black hole. One of the expansions is positive, one of the expansions is negative. It's expanding in this direction, contracting in this direction. way to say it is that the extrinsic curvature is space-like. For these cases, theta k, theta l is negative, and the entropy is less than the area. One other way, the way to think about this is that this extrinsic curvature being space-like is a sort of quasi-local way of saying that the surface is outside a black hole. This is not a terribly precise statement, but it is a good intuition pump. Secondly, you can take the surface to be on the horizon. In this case, the expansion this way is 0. This is a non-expanding surface, and it's contracting this way. These are called marginal surfaces. And for these guys, the product is 0, and the entropy is exactly equal to the area. The HRT surface, which is the bifurcate horizon, is a special case of this, where both are 0. Finally, and most importantly, take a surface inside the black hole. So this is a trapped surface, because it's contracting in both directions. And similarly, there are anti-trap surfaces which are expanding in both directions. These are inside the black hole. And for them, the square root is bigger than 1, which means that the entropy is bigger than the area. And this is the crucial thing that asking the question carefully gave us. Because you can take a surface very close to singularity, and the area is really tiny, but the entropy of the space-time is still the area of the bifurcate horizon, right? And this inequality is the thing that makes this story work. There is a more general story where you don't need to take sigma to be rotationally symmetric, and the answer turns out to be the entropy bound turns out to be some function of an SO2 to holonomy around sigma. This SO2 to gauge field is the same gauge field that turns up in the Chern-Simons formulation of GR. Okay, so now let's add some classical matter. In classical matter, there is more data on sigma. It is the value of the matter field and the derivatives of the matter fields in the two normal directions. So I will specify sigma by the intrinsic metric, the extrinsic curvature, the values of the matter fields, and the derivatives of the matter fields. Okay? So a space-time containing sigma means that it contains a surface that has all of these properties correct. We will assume that the bulk matter satisfies what's known as the dominant energy condition, which says that if you have two future-directed time-like vectors, the corresponding component of the bulk matter stress tensor is positive or non-negative. Okay, so now let's look at the entropy bound. So I've again drawn an ADS Schwarzschild black hole, okay, and I take a surface sigma inside the horizon, and this little red cut, I've drawn it out here. This is sigma, this is the bifurcate horizon. Okay? I emphasize that I'm drawing these simple spacetimes, but the actual results are more general than the simple spacetimes. They work for arbitrary spacetimes. Okay? Now, I have to change my spacetime to maximize the area of this bifurcate horizon, okay, while keeping everything around sigma constant. And a cartoon of the result is that you can kind of add matter in this shape, so there's no matter around sigma. And if it's negative pressure matter, this red cut here develops this little bulge, okay, so that the area of the extremal surface becomes bigger. And you can make it bigger and bigger as much as you want. Okay? So we find that for a surface inside the horizon, which is a trapped run anti-trap surface, the entropy bound is infinite. It is infinite given all the data on sigma. Okay, so this is a more meaningful infinity. That it says that you cannot constrain the entropy with just the local data. For surfaces outside the black hole, the story is not particularly changed from before, and the entropy bound is just the entropy bound I wrote down previously. This is for rotationally symmetric surfaces only. We did not do the analysis in the general case. Okay, so why does this work, and how am I pulling these results out? The answer to both is the same. The answer is that gravity has constraints. Okay, so if you have a Cauchy slice capital sigma, okay, the initial data on that Cauchy slice is a metric and the extrinsic curvatures. The conjugate momentum is some function of that extrinsic curvature. Okay, but if you write down an arbitrary set of initial data, g comma k, that is not physical initial data. It is physical only if it satisfies two constraints. One is known as the Hamiltonian constraint, one is known as the momentum constraint. I've written it down for you in the 3D case and without matter, just for illustration. These two constraints ensure that the classical theory has diffeomorphism gauge symmetry. And basically, these two constraints are also partial differential equations on the initial data, and basically the bounds before come from analyzing these partial differential equations. Okay? So this is the bulk story. So now let me turn to the Cauchy slice story. Okay? So consider a boundary state. Okay, this is a state capital psi into CFTs prepared by some Euclidean path integral, which I've drawn as a semicircle here. Okay? There's something called the Wheeler-DeWitt wave function, which is basically given by taking the Euclidean path integral preparing the state, taking a Cauchy slice with metric G and matter field configuration phi. Okay, the Wheeler-DeWitt wave function is a function of these two, and doing the path integral with these boundary conditions. And of course, doing the path integral just means doing it in perturbation theory around some saddle. So basically, this becomes an on-shell geometry with these boundary conditions. And the action of this on-shell geometry is the Wheeler-DeWitt wave function. The diffeomorphism invariance of gravity is still encoded in the two constraints, but now realized as differential equations that this Wheeler-DeWitt wave function has to satisfy. Every pi mu nu in the constraints becomes a delta by delta G mu nu. Okay? That's how these two things are defined. So a Wheeler-DeWitt wave function is a function of metric and matter field satisfying a few differential equations. Now, the big jump in Cauchy slice holography is to reinterpret the Wheeler-DeWitt wave function. So the Wheeler-DeWitt wave function is the inner product between a ket psi and a bra, which is the state on this Cauchy slice. Okay? So this inner product I have drawn by two arrows. Okay? You reinterpret it as the partition function on some putative field theory that lives on this Cauchy slice, where the metric and the matter field become sources for this path integral. And the boundary state becomes some boundary condition. So this Cauchy slice calculates a transition matrix, and the boundary state is you convolve that transition matrix with the wave function of the boundary state. Okay? This is Cauchy slice holography. And now the two constraints, which were differential equations acting on the Wheeler-DeWitt wave function, are now differential operators acting on a partition function. And whenever you differentiate a partition function, you get an expectation value. Okay? And delta by delta G specifically is the expectation value of the stress tensor. So the constraints become correlation functions that becomes equations that are true within correlation functions. Okay? And a field theory that satisfies these two equations is known as a TT bar deformed theory in 2D. In higher dimensions, T squared or T squared plus OO. Anyway, there are different versions. But in 2D, pure GR is TT bar deformation. This was what Gonzalo introduced very nicely in his talk. You don't really need to know what this theory is. But now I will tell you exactly how we think about the entropy bound from the point of view of the Cauchy slice theory. Okay? So consider again a surface little sigma in some space-time, and consider a Cauchy slice of that space-time. Okay? This Cauchy slice I have drawn here. Okay? Now remember that there is a partition function. This is a transition matrix from the left to the right. So whenever we have such a transition matrix, we can cut it. And whenever we cut it, we get a Hilbert space on the cut. So when we cut it at little sigma, we get a Hilbert space, which I am calling H sigma. This Hilbert space has a Hamiltonian, and you can calculate the energy. In fact, the Hamiltonian is exactly given by the extrinsic curvatures. That's some function of the extrinsic curvatures. In this case, the energy turns out to be area times square root of the product of the expansions. You've already seen the product of the expansions before. Secondly, Space-time is classical. That means that extrinsic curvatures don't have large fluctuations. This means that energy, that in this partition function, energy has small fluctuations. 5 minutes? Okay. So then you do a maxent question given these two data. So you have the energy, you have small fluctuations, so you look for a microcanonical entropy. And we solve things, and we find that the microcanonical entropy at this energy is given by the Cardy entropy of the underlying 2D CFT at some level, which gives you exactly the formula from before. Okay? Now, this energy has a square root. It turns out that the weirdness of the square root, which can be, of course, imaginary as well, real or imaginary, is exactly the weirdness we saw before. Whenever the energy is positive and non-zero, that corresponds to a normal surface, a surface outside the black hole, and so S is less than A. When the energy is exactly 0, that is a marginal or extremal surface, so S is equal to A. And when the energy is imaginary, that corresponds to a trapped surface, so S is greater than A. So the weirdness of entropy exceeding area is the weirdness of the energy being imaginary, and they're related by this duality, this proposed duality. Okay, so this is all I have to say about the boundary story. There are much more details in the paper. So now let me quickly comment on tensor networks. So now we have a path integral corresponding to a Cauchy slice, and whenever we have a path integral, we can cut it up on these red cuts and take the piece between the cuts as a tensor and replace every cut by a set of bonds and call this a tensor network. Okay? And turns out that you can argue that it's enough for the log bond dimension of each bond to be the entropy bound. Okay? So now in pure GR, the entropy bound is the same on every surface that's homotopic to some other surface. Okay? So the tensor network has the same bond dimension throughout. So it's very different from traditional ones where the bond dimension is the area. Okay? So this tensor network has no changes as you go from left to right, which is correct because 3D gravity is a topological theory. There should be nothing there, and there is nothing here. You can add matter, which are these blue dots, and now that the tensors, the bond dimensions change. At the marginal surface is the area. For a trapped surface, it's infinite, the bond dimension. Okay? And an important fact about this tensor network is that it works for any Cauchy slice. Usual tensor networks, random tensor networks, happy code, whatever, work only for slices containing only normal and extremal surfaces and marginal surfaces. This works for all slices with the cost that you get infinite bond dimensions sometimes. Okay, how much time do I have? 3 minutes? Okay. So these tensor networks have only 2 boundary regions. You can ask how to generalize to more boundary regions. So typically, suppose this is a 3 boundary wormhole, okay? And typically the way we build up tensor networks is we tile this entire slice with tensors, which is what Peach and Ross did, and here you should ignore the black parts, okay? But for this, say this surface here gets broken up into 2 pieces, okay? And that is not okay for us, because remember that the entropy bound was some path-ordered exponential of some gauge field. It is not local on sigma. If you break sigma up into 2 pieces, it's not the sum of 2 things on the 2 pieces, okay? So you can't break them up. So what do? The correct way to do this is to, again, all these red slices become bonds, but this pair of pants in the middle becomes something called multipartite edge modes. Like the bonds corresponding to these 3 red slices are actually multipartite entangled. Okay? So now let me make a quick comment on black hole information. This is only for experts. If you take a nice slice in an evaporating black hole, the tensor network vaguely looks like this, okay, where there is this is the collapsing shell, these are the interior Hawking partners, these are the exterior ones. And at late times, the entropy of everything inside is much bigger than the area of the marginal surface on this nice slice. Okay? And this means that this tensor network has post selection at this marginal surface. Okay? So, this is a kind of very vague and sort of hand wavy argument that the bulk boundary map in this context is not isometric, or it has a Python sludge. Importantly, this is something of course that various people have noticed, but the important thing about this is that it never uses, this argument never uses Euclidean wormholes. Okay? So, it corroborates all those analyses without ever using Euclidean wormholes. So, let me conclude. To summarize, I explained a bulk Maxent question that genuinely upper bounds UV entropy on using data on a codimension 2 surface. We found the entropy bound in some simple cases. Importantly, the entropy can be bigger than the area. The Hilbert space dimension of a surface is not constrained by the area at all. Area is just some macrocanonical entropy. There is a dual question in a Cauchy slice theory, which we explained, and there's a duality there's a dual weirdness of entropy being bigger than the area. We obtained tensor networks for arbitrary Cauchy slices, and you can argue for non-isometry without using Euclidean wormholes. Let me make a quick aside on de Sitter, because that's the fashion these days. So, what happens in de Sitter is that the square root has a different sign inside it. Earlier it was 1 plus theta k theta L, now it's minus. What this means is that in de Sitter, for a surface in the static patch, which is a normal surface, the entropy can be bigger than the area. This was exactly what Gonzalo explained in his previous talk. So, some people worry that, okay, with these ideas, the surface is not big enough to hold the entropy of the cosmological horizon, but this analysis says it is. And so, this is important for observer holography type ideas. Okay. So, finally, some open questions. We do higher dimensions with rotational symmetry in the paper. Can we get an answer in the general case? I didn't explain it well, but there's an infinitely big Python sludge. We can use these ideas to derive the holographic map in more detail. I would like to have a boundary interpretation of different Cauchy slices, and we can use this to factorize the bulk Hilbert space, maybe. Thank you.
All right, thanks, Ronak. All right, so questions, maybe in the front.
Do you want? Okay. Anyway.
Oh, yeah, you can be supervised.
Fine. Okay. Thank you for the very nice talk, Ronak. My question was about your first part where you had that maximization procedure. You looked at the minimal surface that was homologous to sigma. Mm-hmm. It seemed to me that the bifurcation surface played an important role.
That's what because that's in my pictures.
Okay, let me just complete my question. Then you can. What if you looked at a black hole formed from collapse, and you went to late times and you took the same surface sigma, the same two sphere? You expect that locally the geometry is the same. But there's no bifurcation surface in the far past. So what do you get for the entropy there? Do you get 0 or do you get the same answer?
If you do a classical analysis, you get 0.
It's 0.
Yes.
So the sigma is somehow 0 in black holes formed from collapse, but it's very different in eternal black hole.
In the classical case, I think so, yeah. It's because, basically like you're ignoring quantum effects. If you include quantum effects, then you get the island extremal surface.
This last part I didn't understand, but somehow you're saying there's some significant difference in
I think
black
so.
holes formed
Yeah,
from
okay,
collapse
good. Maybe I should be more conservative in my answer, and I should say I have not done this calculation explicitly, so I'm just speaking from my gut.
Okay, fine, thanks.
Yeah.
Other questions? Yeah, there's up in front here.
Thanks, Ronak. So when you talked about the de Sitter, you said that you get the minus sign in the square root, but then once we go past the horizon, then obviously now everything's growing, right?
So what happens in the future is that the area is very big, but the entropy stays finite.
Okay.
We share a note on Dropbox that says this.
Okay, thank you.
All right. Ahmed has a question.
Do you by any chance have a prescription for deriving this formula using the path integral?
So in the pure GR case, yes. Like we actually solved the theory, and then you can basically map the states in the deformed theory to the states in the original CFT, and that's how you get the microcanonical entropy.
Okay.
And we have also an abstract proof that the two maximizations are the same, which works even when we can't solve the path integral.
I was imagining along the lines of defining some gravity path integral with some like cosmic brain somewhere.
Oh,
biasing
you're
its
saying a bulk
location
replica
somehow.
trick. I see.
Yeah, like
Oh, I have not read this.
okay.
Yeah.
We have time for one more, I think. Let me look in the back first. Yeah, let's do this one as the new person. Yeah.
Hi, can you comment on how factor theory will be useful? Your last conclusions?
Good, that's a great question. So in this paper, in this beautiful paper out here, they spoke about something called intertwiners, and there are cases, there are upper bounds on the entropy you can write down, which correspond to taking different arrangements of intertwiners, and I suspect that those different arrangements are like different Cauchy slices. I don't know. This is very vague. I should have removed this from before this talk, but anyway, yeah.
All right, so let's thank Ronak again. Now we'll have Geoff Penington, who will tell us about the title that he didn't submit on time, so whatever it is.
Okay, great. So thank you very much, the organizers, for inviting me. So I'm going to be talking about this paper that came out in arXiv a couple of months ago with Adam Brown, Luca Iliescu, and Misa Uchatruk. In particular, I want to advertise how many of the calculations and also the ideas came from Misha. He was a grad student when the project started, and at one point the goal was to get this paper done by the time he applied for postdocs. But in the end, it's done in time for if he applies for second postdocs, which is close enough, really, I think. Okay, so this talk's going to be about a very simple question, possibly the most simple question you could ask in gravity, which is let's take a universe containing a single isolated black hole and ask what happens to it. In particular, by a universe, I mean our universe in the sense it will be the standard model coupled to gravity, but it's not going to be quite our universe because it's not going to have any cosmology. We'll just make it be asymptotically flat. We're not going to have any cosmological constant and so on. And that's going to be important because there's going to be some long timescales appearing in this talk. And by what happens, then I just mean at the most basic level of like roughly what we would see. We're not going to be talking about any subtle effects like information being preserved or anything like that. Just if you're off far away from the black hole, like what sort of energy distribution do you see for photons coming out? So of course, in the 70s, Hawking made his famous seminal contribution that if you do a QFT in curved spacetime calculation, then you see that black holes radiate and lose energy and evaporate. And so long as your black hole is not too large when it starts, this is basically guaranteed to be a good approximation, at least at this coarse grain level, until the black hole has a mass that's order the Planck mass. And then you have a couple of quanta that get emitted at the very end where we don't really know what happens. But they can carry a tiny fraction of the original energy and entropy, so we don't worry too much. But in fact, this has really been known since the early 90s, with a generic sufficiently large black hole, which I'll be more precise about what I mean by that in a minute, then this sort of Hawking-style calculation gives completely the wrong answer. It gives answers that are sort of obvious nonsense, and it gives such answers for almost the entire history of the evaporation process. So the goal of this talk is going to be to do better than Hawking, to not just do QFT in curved spacetime, and actually do quantum gravity in a controlled manner in our universe, and thereby give a correct analysis of this full evaporation until we get down to this Planckian mass where no one really knows what to do. Okay, but just to start things off, let's not worry about quantum gravity and just worry about classical GR. So already by the early 1970s, people worked out the no-hair theorem that says given any black hole, it will quickly settle to an equilibrium solution characterized just by its mass, charge, and angular momentum. So generically, you'll have a Kerr-Newman black hole where the charge is order the mass and the angular momentum is order the mass squared, just by dimensional analysis. At this point, the classical evolution will stop, And the sort of only further changes come about because there's Hawking radiation. It's a very slow process that's basically quasi-equilibrium, where just gradually this mass charge and angular momentum will change over time. So let's start by talking about the angular momentum. This is going to be the only slide where it will feature because Kerr black holes are horrible. So if you have a Kerr or Kerr-Newman black hole, then the Hawking radiation, the photons and gravitons and so on being emitted, will tend to carry angular momentum in the same orientation as the black hole. So they will carry away the angular momentum of the black hole rather than giving it more. And there's a very beautiful paper due to Page in just a couple of years after Hawking's work that shows that, in fact, the angular momentum will be carried away faster than the mass. So if you leave the black hole for a while, let it sort of half evaporate or something, it will have lost more than half of its angular momentum. After not too long, we get down to a sort of Schwarzschild or Reisen-Nordström black hole where the angular momentum is perturbably small. It does not affect the classical geometry. Okay, so that's 3 of the 5 numbers characterizing the black hole ticked off. What about the charge of the black hole? So the key difference with angular momentum that's going to make the whole point of this talk, really, is that all charged particles in our universe are massive, the lightest ones, the electrons and positrons. And this is going to mean that the Hawking radiation is going to be exponentially suppressed at low temperatures. And yeah. Okay, so at low temperatures, massive particles can't be produced. But charged particles can still be produced, even if the charged particles are massive and the temperature is 0. That's because they're produced via the Swinger effect. So this was already understood in the 50s. So what does the Swinger effect? Yeah, the Swinger effect just says if you have a strong enough electric field that is roughly comparable to 1 over the mass of your lightest particle squared, then you can emit that particle. In fact, you will emit that particle. So the horizon electric field of a black hole scales as the charge of the black hole divided by its horizon radius squared. It's just the same as the Newtonian formula, which means roughly that it's the charge of the mass squared. So for a very large black hole, this electric field starts to get quite small, even if the black hole is extremal, and so its mass is comparable to its charge. When this charge gets big enough, it needs to get bigger than about 10 to the 44, or about 10 to the 6 solar masses for an extremal black hole. This electric field gets small enough that the Swinger effect itself becomes exponentially suppressed. At this point, so black holes with this incredibly large charge, and this is really, this is a charge that even if the black hole was extremal, would need to be basically a supermassive black hole, maybe 1% of the mass of the black hole at the center of our galaxy. But if you had a charged black hole that was that big, totally possible in an asymptotically flat universe, then it would lose mass through the radiation of photons and gravitons, but it wouldn't be able to lose charge, or at least it would lose charge exponentially slowly. Okay, so what would happen then? Mass will go down and down and down, and so the black hole will get closer and closer to extremality. As it does so, it will get colder and colder. In fact, its semi-classical temperature scales as the square root of the mass above extremality. That's a typo. It should be m minus q. In particular, this was first pointed out in a paper by the 90s by I think, Wilczek and Preskel and people. When it gets smaller than 1 over the charge of the black hole cubed, then the temperature becomes larger than the energy of the black hole above extremality. This means that a single thermal Hawking quanta would apparently contain more energy than the energy of the black hole above extremality. This is clearly nonsense because apparently we emit a single black hole and it becomes super extremal. So this is a signature that this sort of approximation we're doing of just doing QFT in curved spacetime is breaking down, because the whole way we made that approximation was that the quantum fields weren't meant to change the geometry, and clearly we're seeing we are, because it emits 1 particle and it becomes super extremal. So that's a sign that we need to take into account things like the back reaction of Hawking quanta, metric fluctuations, and so on. There's actually a sort of more simpler way you can see that as we approach extremality, then the geometry of the black hole is sort of becoming fluctuating, is losing semi-classical control, without talking about actual super extremality. And that's just that a near extremal black hole has this very long throat, that looks roughly like AdS2 cross S2. As the temperature goes to 0, the length of the throat diverges to infinity, and so very small changes of the boundary conditions, just a tiny change of the energy infinity, are leading to very, very large changes of the geometry. That's a sign that you have the back reaction is becoming important, and basically what's happening is that the geometry has almost 0 modes where you can have very large changes in the space-time geometry while still remaining very, very close to being on shell. Okay? So back in the 90s, when people were first thinking about this problem, then I think probably, I wasn't there and it's not entirely clear from the papers, I think probably they were aware that this sort of back reaction was an issue, but it didn't seem like you could do anything about it. Like quantum gravity with non-perturbatively large fluctuations is just beyond our control, and so there wasn't anything terribly much you could do. But what we now know as of the last 10 years or so is that these almost 0 modes have a beautiful effective two-dimensional description, which is basically JT gravity plus an SU2 gauge theory. And those modes form a solvable quantum mechanical theory. So I haven't included citations, but I think most people here know them. They're all very famous at this point. But we've gradually come to understand that you can just solve this system exactly. In particular, it becomes Schwarzian quantum mechanics, the same as the effective field theory of the SYK model, coupled to a quantum rigid rotor that's just covering the SU2 rotations. Okay, so our strategy then for trying to do better than sort of naive QFT and curved spacetime is to take these almost 0 modes and the matter fields that were already treated quantum mechanically and treat them in full non-perturbative quantum description. Okay, so we're going to exactly use the Schwarzian quantum mechanics and the quantum rigid rotor, treat them fully quantum mechanically. Then all other space-time fluctuations, like fluctuations out here far away from the black hole, we're going to treat perturbatively, just as usual, perturbative graviton excitations. So this was originally done, by the way, to understand the thermodynamics of a near-extremal black hole in the seminal paper by Luca and Teriachi in 2019. And what you find when you do that is that this Schwarzian physics in particular, the Schwarzian quantum mechanics, dramatically changes the thermodynamics of the black hole as you get very close to extremality. So Luca and Joachim just considered theories where you have no light matter fields, so they were not talking about Hawking radiation, but they just wanted to understand the thermodynamics and sort of Euclidean path integral calculations of the entropy and so on, and see how they change close to extremality. What you find is that the semi-classical relationship between energy and entropy that I showed before dramatically changes. And in fact, when you're below this breakdown scale, then the temperature becomes linear in the energy above extremality. So that's much better than we had before. So now, sort of a typical Hawking quanta that maybe has energy T would not actually take the black hole to be super extremal. It would be okay. But of course, thermal physics, you don't always have an energy of exactly T. You have an energy of order T, but with fluctuations. So pretty often you're going to see thermal photons that would take you super extremal. So this is not enough on its own to fix this original problem posed in the 1990s that Hawking radiation was inconsistent. On the other hand, now that we're not doing QFT and curved spacetime anymore, we're trying to do quantum gravity, it's not at all clear that the radiation even should be thermal, so the fact that the thermal photons could violate the extremality bound doesn't seem as important anymore. So the obvious thing you've got to do is just go ahead, do a calculation, and actually compute this radiation spectrum and see what happens to the black hole and whether we fix the problem or not. So that's what we did in this paper. So I said this paper was just going to be about our universe. This is the one slide that isn't. Let's just think for a moment about the toy example of just a single massless scalar field. Okay? So what happens semi-classically here? Well, as we all know in Hawking radiation, you have near-horizon outgoing modes, outgoing Windler modes that are in a thermal state. Then you have some one-dimensional quantum mechanics scattering problem, and then there's some probability that those modes make it out, and they become thermal Hawking radiation multiplied by some gray body factor, and then the rest of the modes just get reflected back into the black hole. So this figure this beautiful work of art of a figure was shamelessly stolen from Dan Harlow's wonderful Jerusalem lectures from 2014. For junior people in the audience, you should never do that for two reasons. Firstly, because it is ethically wrong. And secondly, because apparently when people get tenure, they have nothing better to do with their lives than send passive-aggressive text messages to you complaining about how you stole their figure. Okay, so as I said, this is an undergraduate quantum mechanics problem. But in general, it's not a solvable undergraduate quantum mechanics problem. All you can do is solve for these gray body factors numerically. But happily, we're in the near extremal region. And in the near extremal limit, you can actually solve it completely analytically just by matching different approximations in the different regions. So basically, very close to the horizon, you have ADS2. Thermal ADS2 modes, Windler modes are exactly solvable. In the middle region, you can just approximate omega equals 0 because the potential is much larger. And then off at infinity, you basically just have a centrifugal force, and that's all that matters. And each of those three things are analytically solvable. You can put them together, and you get some very nice answer that the probability of your scalar getting emitted looks like 4 times the frequency omega times r plus squared. So at very low temperatures, this becomes very small, goes to 0. There's very low probability of emission. OK, so now let's try and solve exactly the same problem, but treating these near-horizon almost 0 modes fully quantum mechanically. So what do we have in our theory? We have two sets of degrees of freedom, basically. In the near-horizon region, we have JT gravity. We have our SU2 gauge theory describing the angular momentum. And we have our single scalar field, our matter scalar field. Far away from the black hole, we just have our scalar field and a fixed black hole background. I'm going to ignore gravitons for now. And at leading order, because we've gone to very, very low temperature to do this, the gray body factors got very small, and so these two regions are basically decoupled. The scalar field is sitting in ADS2 and can't get out. Meanwhile, there's modes far away at infinity that are just bouncing off the black hole. They can't get in because they're very low frequency. OK? But we have some very small perturbative coupling that can be computed semi-classically, where there's some probability that if I send something in from infinity, then it sort of sources the non-renormalizable mode of the near-horizon region. And vice versa, if we have sort of modes in the near-horizon region, they can perturbatively source far away from the black hole. And so this gives us some interaction Hamiltonian that you can write down that basically is the product of two things. So here we have, this is a creation annihilation operator of the far field modes that are sourcing some field, sourcing a non-renormalizable mode of ADS2. And so this is just like the usual source you have in ADS CFT. That is then getting multiplied by this operator I've called O, which is the normalizable mode in the near-horizon region of the scalar field. OK, so this is totally standard ADS CFT physics, but we're just doing it for a black hole sourcing this near-horizon effective field theory. OK? OK, great. So now let's actually do a computation. Let's try to compute the scalar field radiation. So this is, again, an undergraduate quantum mechanics problem. You have two systems that are decoupled. You want to see the radiation from one to the other perturbatively in the weak coupling. How do you do that? You use Fermi's golden rule. So here is Fermi's golden rule written out nicely. We start in a state where we just have a black hole at energy EI. We end up in a state where the black hole has energy EF, and we have a photon emitted with a scalar field quantum emitted with energy omega. And it's just given by this formula. You can just plug all of this in. It reduces to some 2-point function in our JT gravity theory. And that is known exactly, has been known for a long time. And so then you can just compute the transition rate and compute the energy flux as a function of the energy of the scalar. So on the x-axis here, we have the energy of the scalar, and here is the sort of net contribution to the energy flux. And what you find is that at high temperatures above this breakdown scale where we started having a problem, then our quantum answer basically exactly matches the semi-classical answer. Everything's good. But then if we go to low temperatures where we got this nonsensical answer that too much, the black hole would become super extremal, we instead get this nice curve that goes down and exactly stops when the energy of the photon carries more energy than the initial energy of the black hole above extremality. So that's all very satisfying. But of course, we don't live in a universe with a massless scalar field. So what do we have? Well, we have photons and we have gravitons. So they're going to be the relevant things we need to calculate the radiation of. And naively, you, or at least I, expected that photon emission would dominate at low energies above extremality, low temperatures, basically because far away from the black hole, you're going to have a centrifugal potential, and photons can carry less angular momentum than gravitons. So you'd expect them to see a smaller potential out there and therefore have a higher probability of tunneling through the barrier. And that would be true if photons were just some random spin-1 field, but they're not. They're the same U1 gauge field that the black hole is near extremely charged under. Turns out that changes things. This is old work, not ours, by various people. And it leads to what's called photon-graviton mixing, where the near-horizon modes are a combination of photons and graviton excitations. And in fact, the mode with the smallest scaling dimension in the near-horizon region is an L equals 2 mode that is a mixture of both photons and gravitons. So this means, sometimes called the graviphoton mode, and semi-classically, because this has a lighter scaling dimension in the near-horizon region, it sort of sees a smaller potential there. That cancels out the larger potential it sees centrifugally, far from the black hole. And this ends up contributing an order 1 fraction of the semi-classical radiation. OK, so that's fine. You can work it out. That's all semi-classical. And then you can instead do the same thing we just did and compute fully quantum emission rates, where you treat these JT gravity modes and the SU2 rigid rotor fully quantum mechanically. Again, we see a nice thing where at high temperatures it exactly matches the semi-classical answer. And then as we get down towards the breakdown scale, we start to see something pretty different going on. But there's something much more interesting that happens with photons and gravitons that doesn't happen at all with scalar fields. Again, it's undergraduate quantum mechanics, namely conservation of angular momentum. So the extremality bound depends not only on the charge of the black hole, but also on its angular momentum. And in particular, for small angular momentum, the minimal allowed mass of the black hole is equal to Q plus something that's proportional to J times J plus 1. This is basically the sort of ground state energy of the rigid rotor if it has angular momentum J. OK, but then if we have conservation of angular momentum, the selection rules say that if we start with angular momentum 0, we emit a photon which has to carry angular momentum at least 1. We cannot stay at angular momentum 0. The sort of thing we want to end up in is angular momentum 1 instead. But we try to do that. We go from some state very close to extremality and go up to angular momentum 1. And we go, oh no, there are no states for us to go to there. So in fact, a black hole sufficiently close to extremality cannot emit a single photon at all. It's just not a thing it is allowed to do. OK, so then what happens? Well, again, exactly the same thing happens in the hydrogen atom. Just take a hydrogen atom with an electron sitting in the 2s orbital. It wants to emit a photon and go to something lower energy with angular momentum 1, but there is no state with lower energy with angular momentum 1. So what can it do? This is called a forbidden transition. The answer is it doesn't do much for a very long time. So if you compare the lifetime of the 2p orbital, which can just drop down to 1s with a single photon, it's about a nanosecond. The 2s lifetime is close to a second. So it really gets very slow, these sort of effects. But it can happen, and the way it happens is by emitting not 1 but 2 photons at once. So this is called diphoton emission, and it can be computed just by doing the version of Fermi's golden rule that you get from going to second order in perturbation theory. So just take your undergraduate quantum mechanics derivation of Fermi's golden rule, combine it with undergraduate quantum mechanics second order perturbation theory, you get this formula, plug stuff in, you get something proportional to the JT gravity 4-point function. It's all a horrible mess, but we're only really interested in the limit where the energies are sort of way below the breakdown scale. And what you find is this nice formula where it has some very, very high power of the energy. So it gets incredibly, incredibly, incredibly slow. OK. So diphoton emission is incredibly slow, but there's something that's even slower, and that's the charged particle emission, because that's exponentially slow rather than just power law slow with some really high power. So how does that work? Well, the point is that you have some electrostatic repulsion that wants to make an electron shoot off to infinity. But Near the horizon, the sort of gravitational attraction becomes even stronger than that, because when you're very close to a black hole horizon, then gravity always wins. And so you end up with this little thermal barrier, so little potential barrier that the electron has to get over, and then it becomes very negative. So the Schwinger effect happens when the electron can tunnel through this barrier, or in fact just thermally fluctuate over this barrier, and then it will get shot off to infinity very, very fast and end up carrying a load of energy. So naively, after emitting the electron, the black hole would have a mass that's just lost the mass of the electron and charge that's lost the charge of the electron. In fact, when this electron makes it out to infinity, it will carry close to Planckian energy because it's been accelerated to ultra-relativistic velocity by the electrostatic repulsion of the black hole. So it turns out when it emits this thing, the black hole does get hotter, but it actually stays kind of close to extremality. So the loss of the mass is almost equal to the Q electron times m Planck, which is what would need to stay extremal. Of course, that's all semi-classical, and we might similarly expect that just like neutral radiation, charged particle emission has large quantum effects from this sort of large back reaction and so on. Certainly, it's having large back reaction on the geometry, so the true semi-classical approximation is completely flawed. So again, you can do this calculation. We did. So you need to take into account multiple effects. First is the gravitational back reaction. So the Schwinger effect is described by some instanton calculation. You can include gravitational back reaction in that instanton basically by gluing a smaller black hole inside a larger black hole. So that takes into account back reaction. I'm getting told off for going over time, but I will go fast. If you zoom out a long way, this back reaction just looks like an effective conical defect. So we end up with some effective 2D description that has a conical defect in there. If we have multi-instantons, we have multiple conical defects. And then we can take into account metric fluctuations as well, just by integrating over the moduli space of hyperbolic geometries containing conical singularities. So at a strings talk, you should include some string theory. So here's how string theory appears in this talk. The way you evaluate these metric fluctuations and sum over all instantons is to use the technology of the sort of topological recursion in the string equation. You do all that, you get some answer for some decay rate, and what actually happens is you get the answer wrong a few times first, and you think you found something interesting, and then you fix various corrections, and eventually you get an answer of exactly the semi-classical Schwinger rate up to some exponentially small correction. So it ends up being terribly boring despite being a very fun and interesting calculation. Okay, so I'm really getting nearly done now, but let me comment on just the last thing that happens is that, so we emit this electron, we get back well above extremality again, and we go back to emitting neutral radiation. It seems exactly the same as before, except something has changed because we just emitted a fermion, so if we previously had zero spin, then the black hole will now have half integer spin. It then emits lots of photons and graviphotons, but they all carry integer spin, so it stays half integer. And that means it can never get back down to j equals 0. So it never gets down to zero angular momentum again. And the best it can do is get down to j equals 1/2. But now, angular momentum selection rules say you're totally allowed to start at j equals 1/2, emit at j equals 1 photon, and stay at j equals 1/2. So this time, the black hole can actually emit radiation still basically as fast as it did before, about 10 to the 700 times faster than it previously did because it's emitting 1 photon at a time this time. So the black hole sort of has this fast cooling phase instead of the slow cooling phase. So just to summarize the whole process, we have this nice little plot here that is not very much to scale, but it captures all the physics. So we start with a black hole that's evaporating semi-classically, emits photons and graviphotons. As it gets below this breakdown scale, it reaches angular momentum 0, and then it has to go via diphoton emission. That's very, very slow. That's the sort of shallow angle on this plot. Does that for an exponentially long time, and then it randomly emits a positron or an electron, jumps back up, goes down again, but this time can't get to j equals 0, and so it drops much steeper, cools much, much faster, reaches a much lower temperature. Eventually, it will go up another exponential time, it will emit another electron, and then you're back to square one. It's back to being bosonic again. So it's sort of this weird tick-tock cycle of like the tick is cooling very slowly, and then the tock is cooling very fast, or vice versa. I think tock should be slow. Eventually, you do this enough times that the charge drops below 10 to the 44. At that point, Schwinger pair production stops being exponentially slow and starts becoming pretty fast. And then what actually happens is that the black hole is driven away from extremality, and it basically reduces the usual Schwarzschild black hole Hawking radiation story until the mass becomes order the Planck mass, and we give up entirely or wait for someone to solve quantum gravity. Okay, so I'm only a little bit over time, so what did we learn from all this talk? Well, we took the simplest problem you could ask about gravity, and we found a fairly complicated story with a lot of different stuff getting involved and a lot of fun. So I guess the lesson is that sometimes, we did this very tricky calculation with neutral radiation, and we found all sorts of crazy interesting physics we didn't expect, like this diphoton emission and so on, and the transitions back in between fast and slow stuff. We also did a very tricky calculation of charged particle emission, and after doing it 10 times, concluded that we almost didn't need to do that at all. It was just completely semi-classical. So that's life, I guess. But another lesson is that there are genuinely controlled quantum gravity calculations that can be done in our universe. Like this, if you get a bit lucky and it turns out to be relatively under control, you can have large fluctuations in the geometry and still control the physics. And I guess the last lesson is that there's a lot of good physics in undergraduate quantum mechanics, so paying attention to that is good. So thanks very much indeed.
All right, well, so I want to maintain a negative number of citation requests here, so I'll point out that one of the M people is here. So if you have a question, Sandeep.
When you contrasted the results from the semi-classical approximation to when you came close to extremality and you had this cutoff.
Yep.
Now, I thought that cutoff would be at, so let's say you're not emitting any charge, the cutoff would be at the extremal mass.
Yes.
But it seemed to be a little higher, or am I wrong?
No. Possibly for the scalar, it would just be at the extremal mass.
Okay.
For the photon, it will be at the extremal mass for the angular momentum after you do the emission.
Okay.
Right? So if you're going to J equals 1, you've got to stay above the J equals 1 extremal bound.
Okay. Okay.
Yep.
Thank you.
Thanks. Okay, maybe Kumaran?
Very nice thought. So at the first stage of the evaporation, you got near extremality.
Yep.
At that stage, we expect the higher derivative terms potentially becoming relevant. At least in the context of weak gravity conjecture, we think they are such corrections that for the weak gravity conjecture to be correct. Are they too small in the context that you're dealing with, or have you thought about those?
Yeah, we tried to work out if we felt there were issues, and we concluded they weren't. In particular, I'm not sure how similar to what you're referring to they are, but there's this work by Gary Horowitz and Jorge Santos and stuff on the effects of higher curvature corrections and how they change the near extremal region as you get close to extremality, near horizon region. And we concluded from those discussions that they were not relevant for the calculations we're doing. Basically because in their case, their claim is that you see something dramatic if you fall in. But if you're just looking at radiation being produced in the near horizon region, then to the best of our knowledge, there's not anything that causes that to break down.
Maybe related to that, if you started at extremality.
I mean, I wouldn't know, what is, literally at extremality?
Yeah, literally, that's the point I'm trying to make, that in the weak gravity, we expect that to still decay.
Yeah,
and then that's where the higher curvature terms become important. That regime was never relevant for your calculation?
Yeah, I think, no. I mean, we're in a regime where, the semi-classical production so the charged particle production is very low, but you're never getting down to sort of e to the minus s temperatures. You're getting down to e to the minus square root s temperatures. I think for what you're talking about, you would really have to be at extremality, but we can maybe talk about it afterwards.
Thanks.
Okay, so Suvrat?
Thank you, Geoff, for the nice talk. Thank you to the chair for not retaliating and allowing extended question time. My question was about the toy model, and maybe it applies to all your models, where you found this sharp cutoff which prevented violation of extremality, and that's of course very nice. The question is, in the Fermi golden rule, is that coming because of the dynamical matrix element you're calculating, or just because the phase space density goes to 0 beyond that? So is it a kinematical effect, or is it a dynamical effect?
So it's there's no states in the quantum JT gravity region theory that have lower than that energy. I think
so it's just the phase space density going to 0. But that you could have kind of put in even without doing a detailed calculation, right? The fact that you should put in a phase space density of final states and there are no states of that kind.
So, okay, you could just put an artificial cutoff. You could take the semi-classical thing and you have some curve going upwards and you just put a hard, sharp cutoff there. I think it would have felt obvious that that probably wasn't completely the right answer even before this calculation, and certainly it would be a very different curve to what we get, including the full quantum treatment.
I was thinking of something more sophisticated, where maybe you put in a density of states which goes smoothly to 0, but maybe it doesn't, Okay, thank you.
Yeah, I mean, you need JT gravity to get that density of states, right? So, yes.
All right, so I guess that's the end of all the talks. There's one person who we haven't thanked yet. My dear friend and collaborator, Ahmed Almiri. Thank you so much for everything. Let's please give Ahmed.